SwayamPrabha. Digital India. Educated India.
So, and now, so that's nice thing. We can see this picture. This is the first buckling mode. We constantly calculate as many as we want. So, for example, if we come to the second mode, then we will see that this looks like this. It looks a bit ugly because of the small number of finite elements. But again, as I said, if you want a nicer representation, you can increase the number of finite elements. The result itself is very stable, so the eigenvalue will not change. What is very important that for each solution of the buckling problem, there are two types of results. The eigenvalue itself is just a number, and once you know the number, then you can back calculate a vector which we can draw graphically like this. But what is the most important is the eigenvalue itself. And what the eigenvalue gives, in this case, if we multiply the eigenvalue of 1.722 with the actual moment distribution of the structure, which is 100 kN everywhere uniform, then we come directly to the critical moment. So 1.72, which is the value given by Consteel, multiplied by the 100 kN, which was the uniform bending moment, then the critical moment is 172. This is the value exactly what we get from the formulas if we are able to use formulas. I did this exercise because for this, of course, there are formulas. So the AISC gives a certain formula.
This is the handout that was posted today, just to make sure everybody understands.
Sorry?
This is the handout that was posted this morning.
Yeah. It was given in a PDF format to everybody. Okay, so it's one thing that we did the calculation by Consteel, but for this we could have done a traditional way. So for this very simple basic case, of course, there are closed formulas to calculate the critical stress. By default, AISC is not calculating the critical moment directly, but it calculates the critical stress. For that, there is a formula which by default looks a bit strange, but this is a simplified formula for double symmetric section. It's very important. It's a typical American thing to make things easier, but the problem is that by doing so, they include in the formula some assumptions which are not visible. So you may have the feeling that you can simply use this formula also for the Z section. No, why not? The Z section has also a E, a P, and others. No, it's not. It's only for double symmetric sections, and that's why it is simplified. So a lot of things are made more compact. How the section formula itself looks like in a more international way, in a bit more uglier way. So that's the way how the formula should be written even for a double symmetric section. It contains a lot of other things. And if you wanted to go for a single symmetric, then it becomes even more uglier. So this is the universal formula if you are looking for a formula. But that chapter of AISC 60 has simplified the formula, assuming all the possible simplification for a double symmetric section. And that's why it came to that format, which gives the chance to calculate directly the critical stress. Okay, so if we are including all the values into the critical stress calculation, then we have a value, and if we multiply that critical stress with the section modulus, then we get almost exactly the 172 kN as critical moment, what we got numerically using Consteel. All these parameters are calculated by Consteel, so I will show how the results are given by Consteel. You can also double check and reuse this calculation. Just for the future, as the AISC gives the critical moment, if we want to calculate backwards what would be the load multiplier, then we just need to divide this value by the uniform bending moment, which was the 100, and we can come to the 1.71. With Consteel, this was 1.72. It's just to give a chance for comparison. Now, also actually AISC has a formula also directly for MCR. I think it's on the next page, but maybe it's in the actual version has been already withdrawn. But it has a formula also for the MCR. Of course, if I introduce the necessary values, it gives exactly the same as the other formula based on the critical stress. Okay? And then I said with Consteel the value is 172, and that gives again the 170 kN. Okay, so at the moment we will not go into to calculate the LTB strength, But let's see how this value changes if we are doing some things with the boundary condition and such. Okay, so in very first step, do what is the most typical situation is that let's use a uniform load on the structure. So go back to constill, to our model, and change the loads. So we cannot delete the bending, the moments. So you can try to click on it. If you are lucky enough that you can click on it, and then it will be selected. Be careful to see that only the load is selected and nothing else. And we can remove it by pressing the delete button on the keyboard. If you are not careful enough and you click not only the load but also the support, and you click on the delete, then you will lose also the support. Okay? But you can also, to be absolutely safe, you can draw also a box around it, a quite nice big box. Obviously, this time the support will be also included. So we need to remove the support from the actual selection by clicking on the red symbol in the line of support to have only the point load to remain, and then we can press the delete button. So now we deleted the load, and now let's place, instead of a point load, let's place a line load. So if you were able to delete everything, then we can define a line load. The line load is the second on the load stop page, not the point load, which we used up to now, but the next one, line load. When we click off line load, then we have a similar screen like we had before. And now again, we want to define the load in the Z direction, and we can keep the 10 as what is the default 10 kilonewton meter as a starting value and 10 kilonewton meter as an ending value. This will create a uniform distributed load. Okay? And we click on the member. What is already interesting here, I didn't speak about, but we will come to that. If you just place the load, the linear distributed load on the structure, then as you can see, its reference is at the reference line of the beam, which is the center of gravity of the beam. So if you are happy with that the beam is acting on the center of gravity, which is the self-weight of the structure, of course, but the other loads are typically not in the beam, but they are above or below or somewhere. But now at the moment, if you don't define any load eccentricity, then by default, everything is understood on the reference line. So we place the load here, and then we do nothing more than just go to analysis, and we can now this time already press the first button because we don't want to change anything else. We just change the load. We run the calculation, and we have now another buckling mode. It looks similar to the previous. Probably there's no human being who sees the difference between the uniform and the parabolic, but the value is different, and now it's 441. 441 means that, be careful now, the bending moment is not uniform. Typically what we say, if you want to use the critical moment, we find the biggest bending moment, and then we multiply by 441. Actually, the question can come, what if we don't multiply the biggest, another? Then we have another critical moment, and we can have as many critical moments as many points on the structure. We can have even 0 if we select the 0 at the end, and we multiply it with 4. So that's how clearly show that the critical moment itself is not necessarily a good measure, because it refers to a certain point. If everything is uniform, it's fine. But if it's non-uniform, like typical structure, it's not a standalone value. It also is a critical moment where. That's why we will see that we are not using the critical moment itself, but something more general. Okay, so now if we want to see how is the bending moment diagram, come to first order, and instead of deflection, select internal force mx again, and then we can see the bending moment diagram here. Sorry, I had another model open, and that which had more. Wait, I quickly I close this. I had another model on my computer open, which had. Okay, now the 10, and if we come to first order internal force mx, we see the bending moment diagram. We can increase the scaling of the diagram representation by sliding the slider left and right. And to better see the reference line itself, we can go back to the simplest representation to have just the line view. In this case, we don't even show the cross-section, just the reference line. And in this case, all these diagrams are the best visible. Okay? And in the middle now, the bending moment is 45. The biggest bending moment is 45. So we could say that the critical moment now is 45 times the first eigenvalue, 4.41. Now, if you go to the traditional solution and use the formula to calculate M critical, now you will need to use the CB factor, because the formula itself without CB gives the critical moment for the uniform bending moment. If the bending moment is non-uniform, then the way how to make the transformation between the stress distribution is with the CB factor. It's interesting, AISC calls this as CB, but for example, in the Eurocode, this is called C1, and maybe, I don't know how is that in your standard. And typically, this is not a new thing. There are typically big tables available for the most commonly found situations, like uniform bending moment, then everything is 1. Then we have a uniform distributed load, and there is this variable of 1.132, and all the different situations. Surprisingly, there are no tables for the combination of the cases. So if you have a combination of moment generated bending moment diagram plus some uniform load, so that means that then you have the combination of the two. For those, there are never tables available. So then the engineer, if he wants to use the tables, then needs to find what is the most dominant type of effect and try to find values from the tables. The use of these tables is very complicated, but this is an alternative. In Eurocode, there are no formulas. The AISC has a formula for the CB. It gives similar results to the tables of the Eurocodes and also other things, but not necessarily exactly the same. Okay? But you need to use the value in order to have to the hand calculation. Here I use the CB value of AISC, which comes from this very well-known formula, this one. Again, important, this is only applicable for uniform cross-section, as we will see later. And if you have seen the design guide 25, this basically, is misleading. The formula speaks about bending moments, but actually it shouldn't speak about bending moments. It should better speak about stresses at certain positions. So if I have a non-uniform cross-section, of course, the stress distribution will be different. That's the reason why we use tapered columns to somehow equilibrate the stresses along the member. So if the tapering is well done, then we can have maybe constant stress on the compression flange. So these CB factors are really for uniform members. But in this case, we have uniform member. I calculated 136, this value 1.136. Simply just multiply the critical stress with this value. I have a value. And then if I multiply with the Sx, then I have the critical moment. The formula itself gives the critical moment itself, but the critical moment itself is understood as the biggest bending moment multiplied by the critical value. If I calculate it, divide it by the biggest bending moment, I have 4.33, and the value which we got by Consti was 4.32, so it's close to that. Okay? Now, what happens if I move the load to act on the top flange? That's already something interesting, because that's not too often studied by design standards, but of course the engineer can have that feeling that the load is really acting. Of course, in reality, it's always a good question that where is the load coming from? If the load is a big fat bird which is sitting on the beam, then it's really a load without support. But most of the loads are load and support at the same time. So if you put a concrete deck on the structure, then probably that is also giving some support. So really the load is acting on the top flange, but it also gives some lateral support if it is well braced. And then there is this distortion of the profile when it gets torsioned. So there are certain reasons why AISC doesn't really handle this with visible importance. For example, Eurocode clearly calls the attention that this is important and need to be considered. Now, in Consti, it's very easy to see if you want to consider it. You click on the load, and you just change the position where the load is acting. Maybe I better delete the load just to better see how it's more visible when the load is when you define a load and not just modify it. So I select the load, click the delete, and I come back to the line load icon, and I keep everything a -10, but here on the load eccentricity, I don't keep the default reference line option, but I click on the 3 dots. In general, in Consti, everywhere, if you see 3 dots at the bottom, that means that there are some specific settings to that functionality. So if you click on it, then you can see such a picture. where there are some specific points of the boundary of the profile shown. And if select, for example, this point here, that means that the load will be assumed as if it was acting at this point of the cross-section. So that means at the level of the top flange above the center of gravity. So I don't need to calculate how many millimeter is that or nothing, I just define it. If later on I change the profile into a bigger one, this will automatically be updated. So this is a dynamic definition. It means that put the load to the actual top level of the actual profile. If I change later on the profile into another one, I don't need to modify. So this is not a hard-coded millimeter, but it's the information is saved. Okay? So the load is top middle, and I click again, and now visibly the load is really placed on the top flange. We can change easily the way how we show in which direction we show the structure by going to this third option. It's very nicely visible. The load is really acting here. Again, it's misleading. Many softwares are misleading because many softwares have the option to accept the load position. Some softwares are only doing to nicely draw it to the exact location, and in some software it has no any effect on any of the results. It is just only to show that it's there. Some softwares, I don't want to blame competition, so I will not say names, but some softwares will try to consider the effect of the load eccentricity in the design verification, but not in analysis. So when you do just the analysis results, everything remains the same. Of course, they cannot calculate critical moments. They follow traditional approach, so there's no problem. But in the analysis model, it's not considered. But that's the big difference in Consteel. It is considered in the analysis model. So we don't make tricks in design later on. We consider it in the analysis model. And if anything like this has an impact on the calculated critical multipliers, then of course that will directly automatically consider. So there's no need to do any tricks later on. So the load is there. And I just simply run the calculation again without changing anything. And now I see that my load multiplier got lower because the load, if it's acting above the shear center, then it is creating an additional torsional effect. If the load is acting at the bottom, when there is a torsional effect, that moment goes into the opposite direction, and the load application point, and the twist which is created has a stabilizing effect, so it puts it back. So if I put the load on the bottom flange, I will see a higher critical stress. If I put the load on the top flange, I will see a lower. And this comes automatically from Consteel. Now, how can that be considered by AISC? It's not very well known, I think, to most of the people, but there is an additional book often referenced, the Stability Design Criteria for Metastructures. And that book contains a lot of those subjects which are not found in the code or neither in the commentary section of it. And for example, there is a combined formula to consider the effect of load height effects, and in addition, whether there is in the bending moment a double curvature or not. There is this quite interesting formula, and here if you introduce in this formula for the given problem, then this means that the default 1.136 will change into 0.8. So the CB factor will be less than 1. Okay, so the CB factor can be also lower than 1. Now, if we put this 0.8 into the formula, then we have of course a lower critical stress than we had before. If we multiply by the section modulus, we have directly the bending moment. If we divide with the biggest bending moment, of course the biggest bending moment doesn't change, it's still 45. We just move the load up and down. It has no impact on the bending moment. So then it will be 305. And now, as you saw that when we did the calculation with Consteel, it was 299 in my case. So it's not exactly the same, but very close to that. Okay, this is a precise numeric solution. The AISC value is based on a formula which was fitted on some, I don't know what. Okay, and then we can continue.
There's also an option where you can put that load above the flange if you want, right?
Yes, we can put in addition.
Eccentricity.
Yeah, so we can also not just use this point as we wanted, but we can, again, I delete it because it's a bit more visible when I define. So I can say top middle, And then in addition, I can specify additional shifts by offsets. So I can say that it's 200 millimeter above the top flange. So in that case, I said an addition 200, and it will be even higher. I could move it also to left and right. So for example, if you design crane beams, in a crane beam, it must be assumed that the load has a certain eccentricity, and that will immediately create a torsion. So we can easily place the load at the right location. And it's important, this is not a picture, this is not only a nice graphical representation of the offset, but it's really something which is considered in the calculation immediately. Of course, if we put an eccentricity, we will have torsion, and because of the use of our 7-degree freedom limit, we will have immediately the warping by moment diagrams and also those strange units and everything else. I will not go into this now. Okay? Now, the other thing what is logically coming into this game is that what happens if we have lateral supports. If we have lateral supports, we still have we go back to the original model, 6 meter long end moments at the two ends, but what happens if we have a lateral support? I just quickly show what I do to have that model. So another matter, it's apparently I deleted everything, so I have nothing more, so I put back the point loads at the two ends, plus 1000 at the left end, not 100, minus 100 on the other end. That was the first example what we have, just to check that we have the same result, 170 is fine. And now I will want to put a lateral support. Let's assume that this lateral support is acting only on the top flange. Okay, this is already something interesting because this is not a fork support. So again, I go back to point supports. I want the support to act in the global Y direction. That means perpendicular to my beam. For this, there is a predefined category which is called Y. And I immediately set the eccentricity of the support. I say that the support should act at the top flange level. And then I can switch off so Y and top middle. I keep the others at 0. Okay? In order to better see the reference line and better see specific points along the line, I switch off this nice or not nice representation of the beam just to have the reference line. And when I come close to with my mouse cursor on the line, what you will see that there are automatically some points pre-marked by constant. These are the quarter points. How many are? You can change it here. So these are quarter points because n equal 4 is the default. If you change that, then you will have more. Now we want to put the load in the middle, so we just select, we go close to the line and click on it. If I click close to the line, I see there's such a bit strange symbol is placed, which is not very much understandable at the moment why it's like that, but if you switch on again the representation of the beam, then you will see that this is really exactly on the level as it should be, and this is now on the top flange. And again, I do nothing more, and I just run the calculation without changing anything. And now we will see that the first buckling mode was without support was 172, and the second had an S shape with 602. Now the first has the S shape with the same 6.02. So that means that here at this moment, the support on the top flange is an efficient support because that is the flange under compression. So even if this is not a fork support, it can be assumed as being equivalent to a fork support. If we calculate numerically the critical moment, then again, we have the 100 kN uniform bending moment. The eigenvalue what we defined was 6.02, so that means that the critical moment is 602 kN. If we want to go the traditional way, then we use LB divided by 2. The LB is not 6,000 anymore, but 3,000. By hand, it's not so easy to verify if the support was really efficient or not, but it's quite evident that the support on the compression flange acts like a fork support. So we can simply just divide the 6,000 by 2, so 3,000, and we put the 3,000 in the formula, we get exactly the 602 like we had before. And then what happens if we move the support from the middle? That's already something interesting, because if we move the support from middle, in constant is very easy. We select the support and move. We can select the support. Now it's selected here with this parameter. And on the right side, I can come to the Move Selected Object command. I click on it. The support must be pre-selected, okay? So the easiest is to select with the box from left to right. If you select from right to left, then it will not be only the support, but it will also be the beam. In that case, you must remove the beam just to have the support there. Okay, you come to Move Selected Object, set the base point for movement. We click the positioning points of the load. And then again, I could click anything else here on the left or right, but if I just want to move by 1 meter, I can also do that. I click the X key button on the keyboard in order to become this active, this field, and I can type here 1000. So that means that from the actual moment with the relative offsetting using the coordinate system, I can say that move the point from the selected towards 1000 in the x direction. And I press the enter and the load is supported. And now it's very easy. Again, I just recalculate. I do nothing more. And now I come to a value. What is an interesting value? So two profiles would have a different, it's no better. A different end rotation, and basically the structure would need to break. Of course, the structure doesn't want to break. The two cross sections will start to play, and based on who is stronger, stiffer, we'll have an agreement finally on what is the equivalent umbrace length. So actually, the real calculation is not 4 meters, but we would need to create an equivalent umbrace length. So the physical length is still 4 meters, but there would be a need to invent somehow a K factor, which would be in this case bigger than 1 to come from smaller than 1 to come from the 4 meter down to something like 3.7 or 3.8, I don't know what. Now again, if you look back to the same book, what I have already mentioned, this stability design criteria for metal structures book, it has a proposal to how to consider this effect. It's not a closed formula, it's a certain step of calculations, but it can be done. It's quite boring and of course practically impossible, but it can be done for such an example. And by doing so, you can find out a more or less valid less than 1 K factor. What if you introduce into the formula keeping the biggest 4 meter as the LB, and then you can come to something intermediate situation. But you can also see here clearly that what happens is that the constant buckling curve for the 4 and 2 meter is not symmetrical. It's visibly the curvature is different. This can be understood as if I was putting here a spring which doesn't let the curvature to be as high as it would be assuming a free boundary condition. This spring value is the neighbor element, the bending stiffness, lateral bending stiffness of the neighbor element. Obviously, if I put a value into my model, my critical stress will be higher. But how to calculate the spring, it's not easy. But if you use constant, there's no even need for that. You just build a model, and then you calculate it, okay? And now, once we did so many calculations of different strengths or critical moments, how we come to a design strength, because it's nice to calculate critical moments, but obviously that's not the name of the game. So if we draw the curve based in function of slenderness, then we have this plateau part where we have the full cross-section strength without any reduction. That is valid for short members with low slenderness. Then on the other end, we have the members with the long members with the high slenderness, where AISC adopts as strength the Euler moment, the Euler stress value. And then there is this intermediate part, which was also part of the discussion, whether this should be moved or not with the CB, or yes, then just simply by multiplying, or not, or doing something more. Now, as this course is mainly about metal buildings, which have typically slender webs, and for slender webs, even in the Design 25, it was basically said that, first of all, the CB is typically not as beneficial as for a uniform section if it's calculated correctly. Second, this increase effect is probably cannot be really reached as efficiently as case of a hot-rolled beam because of deformations due to the shear. So the slender web will suffer deformations, and ultimately it will not be able to reach as high strength as without such deformation under the stress gradient it could reach. So therefore the general recommendation of the Design Guide 25 is that in case of slender web structures, don't take any additional CB multiplication except that what is in the game immediately. Because don't forget, in our sigma F critical calculation, the effect of stress distribution is automatically included. So I changed nothing, I just placed the distribution of the load and I got immediately always the correct critical moment value. So that means that all the built-in impacts of the stress, these different stress distributions are in the value. An additional, a bit artificial multiplication is not recommended in case of slender webs because the positive impact of this additional positive impact in this intermediate slenderness section cannot be reached due to the difficult to take into account but existing deformations due to web shear. It's also important such modifications exist also in the Eurocode and therefore also I guess also in the Indian standard. It still doesn't have, it's not as relevant as in the AISC, but it's called a small f, I think. So the effect of the stress distribution has a direct impact, a beneficial effect on the strength, but by far less important than by AISC. Okay, so in this example we will do nothing more. Sorry?
I don't think the Indian standard shows the
Shows what?
The F parameter in your code
No.
that gives you some additional help from moment gradient.
Right,
That's
no,
not there in the
yeah,
Indian.
that's...
It's not in the Indian code?
Yeah.
That
Okay.
was in the-
Okay, so then you are fully in line with these.
Yeah.
So no any other consideration, although something could be, but it's a bit foggy. And in case of slender webs, probably that could be equal to 1.
And there's the shear reduction that we're doing now on the LTB resistance, which is a bit painful. But we're proposing that if the calculated CV from design equations is less than 1.4, that you don't need to do
Then
it.
you can neglect it, yeah.
And for when you have a web taper, it's very, very rare that you're gonna it's kind of complicated to even calculate that CV.
Yeah.
Once you calculate it.
Yeah, to calculate the correct CB for a tapered member is difficult.
Yeah.
It's better not even to start it.
Right. Right.
So actually, you don't lose that much as you might expect.
Right.
But certainly you lose something. But here we assume that Consteel cannot take that into account because Consteel does everything automatically and Consteel reads everything from the linear buckling result. It doesn't have this additional artificial, this human type of thing that, okay, what is the member length? We don't know. We just saw with the example the member length itself is a bit, it's not always the physical length. It can be modified by something. If you have we will see when it's non-uniform question, again, the length, it doesn't really have a real impact. So to calculate the CB, it's defined that you need to know the length. If you don't know the length, you have no even any chance to, even if it's complicated or not, you cannot calculate because you need to find the bending moment or the stresses at the quarter points between your arm brace lengths. But if you don't know what is your arm brace length, simply because you cannot find fork supports, then there is no arm brace length. Or you have fork support, but you have a trapezoid sheeting on top of it. Then what is your arm brace length? Still the one without the trapezoid sheeting? Probably not. You would need to find an equivalent arm brace length, and not just to have a shorter one, but you need to also position it correctly around your critical point because you need to find the quarter values relative to I don't know what. So it's not easy. Consteel cannot do that. Consteel does everything numerically. These sort of human cheats are out of reach. Okay. So once we have drawn the LTB curve made of the 3 lines, this time already everything is defined in function of slenderness, so not on length anymore, but based on slenderness. It's fully identical, almost fully identical to the length-based definition. And then what remains is very easy. Again, as I have shown at the beginning, that how was the flexural buckling calculation. We know the slenderness, we know the reduction. Again, we do the same. we always have the same cross-section, so the curve remains the same for all the games, all the exercises we did up to now. What was always different is the critical stress or the critical moment. Obviously, that means that the slenderness will be different because the slenderness lambda LT is defined as NYC, the section bend, the cross-section, the critical cross-section bending moment divided by the critical moment. And then for the different type of cases, what we did for the uniform bending moment, we got the 172 kilonewton meter. If we calculate the lambda LT of that, that would be 1.41. And if we put the 1.41 into the curve, then we can read the corresponding reduction factor, which will be around 0.5. We multiply by 0.5 the cross-section strength, we have the LTB strength. For the other case, when we had the load on the center of gravity, the critical moment was 194. For that, we have a somewhat lower slenderness. For the somewhat lower slenderness, of course, we will have a somewhat higher He value, and we have a higher bending LTB strength. Then when we move the load to act on the top flange, then it has a detrimental effect. As we know, the lambda got increased from 1.32 to 1.6. For the 1.6, we will find the lower value of the He. Then we place the intermediate support on the structure exactly in the middle. Then we found a very high critical moment for which we find again another value. And then we move the support to be not in the middle anymore, but offset it by 1 meter. Then again, we found another value, and we have another strength. So basically, the whole process can be fully automated. Me, as a user, have never entered no one single value of K factor. I didn't tell to the software what is my length. I didn't even say that I have a fork support. I defined a fork support, but I could have easily changed, instead of the fork support, just something which is defined by a spring, so then a linear spring, so it's not rigid, it's just relatively rigid. And of course, you can imagine if you change something, everything is just a big stiffness matrix. There are values there, and we make a mathematical calculation. If you change the values, the number will change. And how? We don't know, hopefully in the correct way, but obviously every change has an immediate direct impact. And this is not based on the way that you find good formulas in the books or not. Who knows more books from the past? You know, in the past, it was always a good engineer could be recognized as having a huge library in his head. Yes, I saw a book 20 years ago for this or that. It's not needed because this can be calculated, okay? And now what happens, for example, if we still stay with the uniform element, but we want to put a trapezoid deck. It's very often, again, for a metal building business that it comes from the same hand, the primary, secondary structure, and also the sheeting. And of course, if the sheeting has some stabilization effect, some possibility for that, why not take into account to reduce the steel consumption? Obviously, it's not very rigid, but it has something. It's non-zero. Again, with the concept, stiffness matrix values, if I put something non-zero, it will have an impact. So why not try to do that? So again, with the same game, I will not show this now because it's, I don't know how much time we have. But we can define also a shear panel. There are certain parameters. We have catalogs of commonly produced panels, but also the parameters of corrugation height and distance of ribs and such can be defined. And then constantly.
Details on that.
Sorry?
I think you're going to do some details on that on bracing.
Yeah. There will be more on that. So then the shear strength, so the representative value of that can be calculated. It's again different in the AISC concept. It's called as G prim, and that has a certain certain formulas. Plus also there is this SDI manual, which gives quite a lot of data for different type of panels. So this is quite heavily used. But on the other hand, it's very interesting again because I don't think that is very much used in practice. So I don't know if those books of SDI are really used by engineers or not, because I think traditional softwares are not really compatible with those information. Now in Eurocode, this is called S, a big S, probably for shear, or I don't know what is in the Indian standard. If there is anything for that, it's probably not too much because this is in the Eurocode 3134 code form, which hasn't been implemented in India. But anyway, so it's a mechanical something. That's the representation of the shear stiffness.
And we've got some people here doing research on stuff.
Yeah, I'm sure they know more than me about this, but anyway, so if you know the number, for conceal, it is just a number, but you can put into the game. Again, you can position that the shear field is acting on the top flange, bottom flange, or even above or below. Doesn't matter. It's just an eccentricity. It's not just graphical representation, but it's reality. It's really considered that way. And when you put it into the game, then it will have its impact. So I just entered here a 1 millimeter thick, it's very thin, 35 millimeter deep panel with some very default basic values. And again, the critical load multiplier from the 1.72 for the uniform bending got increased to 7.12. So that's a 7 times increase, no, maybe 6 times increase of the critical moment. Of course, it doesn't mean that my LTB strength will be 6 times bigger. No, it doesn't mean that. It only means that my slenderness will be somewhat different. It will come under the square root, so you can expect that 6 times bigger maybe will be a 2 times bigger or 2 times smaller slenderness, and depending on how, in what slenderness range we were originally compared that, we will have a much lower critical stress. And then if we calculate the slenderness, larger critical stress and smaller slenderness. So for that here, for this case, the HELT will be only 0.9, and that means that we are very close to the cross-section strength, but we are less. So again, this typical assumption, I put a sandwich, a trapezoid, and I don't need to check anything, it's not necessarily true. It has a big impact. But finally, the LTB strength will be less, 10% less than the cross-section strength. So very often people just believe, it's typically there's no calculation. In some standards, there are some formulas which define the minimum parameters of something which can be assumed, and then you are allowed to disregard, for example, LTB. So if you are sure that your panel is strong enough, then you can disregard LTB. Now these rules, how precisely are defined, difficult to know. But again, what's the problem if you have a panel which doesn't fulfill those requirements? Then its effect is 0. Of course, it's not 0. It's just less than 100%. Now here you can easily consider and everything. So you don't need, and that's what we see later on when we come to the bracing problem. AISC is smartly full of such limitations to avoid problems for a hand calculation. But again, always the problem is that if you can reach it, that's no problem. If you can reach those stiffness requirements, it's no problem, and then you can do the calculation. But what happens if you cannot reach due to technical reasons, or you just don't want to spend so much money? And you believe that half of them is also enough for a smaller impact. Now, that is unknown in AISC. So full or nothing type of game, like typically everywhere. Also, this is a sort of, also in the all German standard, they defined, also in Eurocode, basically, they define the minimum value of S. If the panel is stronger, then you can exclude in your calculations LTB. If it is less, then no one tells you what to do, probably nothing. Then people either select a stronger panel or they disregard the effect in the calculation. Now, if you work with constant, there's no such thing. There is no black and white anymore. There is just a million combinations of the grays between the white and black, and everything can be quantified. So that's a sort of summary of this part, is that there are two traditional solutions. One traditional and another. The traditional solution is that you can design everything you want as long as you are able to determine the correct K values, and that is called the effective length method. Your structure is divided into basically isolated members. Somehow you are able to transform the boundary conditions into this single element. It's not explained how. You can apply some K factors, or you can say that by default you take 1 and you believe that it's on safe side, sometimes not even on safe side, but probably it's yes. Then regarding LTB, there is also this problematics of the CB, which again, it can be calculated. In case of a wet taper member, it's more difficult to calculate, but can be still calculated, or you can take it as 1 to get a conservative result. But even then, so this is the traditional approach, and what we could achieve with not with consti, but this is not of consti. This is a possibility that everybody else could do. That we base everything on numerical results, and there's a huge benefit of that there are no more members, there are no more lengths. We can completely forget all these problems of the k factors and such. Nothing. You just build a structure and you calculate, and everything is considered not just by random numbers, but by a mathematically adjusted approach. Everything is handled through the critical stresses, which can be calculated precisely. We will see later on that not only for pure compression and pure bending, but in case of combined situation, we have a structure which is exposed to bending plus compression together at the same time. That combined effect can also be considered. So we can calculate critical stresses which are not for these isolated stress distribution, but for the actual situation as it is. No separation, nothing is needed. Everything as it is. What is important, build the right model. If a load is eccentric, then the load must be in the model eccentric constant. We never know that the load is not there where I defined. It reads only the model, the supports, everything must be at right location, and after there's no more to do. Really no more to do, just run the calculation. And that's I believe it's a fantastic possibility, especially for those who recognize its importance. Many people don't recognize. It's very disappointing. I saw videos on the YouTube. It's full of such videos, especially if you look for meta building design. That's amazing. That is considered the simplest part of the world, how to design a meta building. The guys always say, there are also a lot of Indian language videos and Arab and other videos. Many people I think they buy a camera and they make a video, and it's good. And they always say that purlin, it's very easy to design. Purlin distance 1.5 meter, so the arm brace length is 1.5 meter. It's easy. My God, no. Only if, but that if is not even checked. So it's not true that it's always 1.5. It depends on the type of roof system. It depends on the stiffness of the purlin, and depends on a lot of things. And 1.5. Now, no. But if you use consteel, it's not even 1.5 what you have in the model. You don't even enter the 1.5. Nothing. Just build the model. If your purlins are 1.5 to 1.9, but doesn't matter what you want, then it will be that. So it's okay. So these are two different concepts. The first is the past or the present, and this is the very general thing based on the use of closed formulas and these very traditional definitions like umbrace lengths, effective lengths. That's a very, very well used in every standard of the world. It's used, but we can have something better if we use computers. By hand, this second approach doesn't work. So to calculate critical stresses for these sort of non-standard conditions, it's impossible. Okay?